Hi, this is Solid States part 1.2. In this we'll study about crystals, crystal lattice and unit cell. Okay, now let's study about crystal. Now the question is, why study crystals? Because crystals have symmetrical shape and they have a regular arrangement as compared to amorphous solid. So that's why we study crystals, because of their arrangement. So we have something to study. There is an order to it, so that's why we study crystal. So crystal is obviously crystalline, so from crystalline comes crystal. So what are crystals? So let's look into crystals. These beautiful crystals, they have regular arrangement. So crystals are solids which have regular arrangement. They have a symmetrical arrangement as compared to amorphous. Amorphous don't have any regular arrangement. Alright, so crystal is derived from Greek word crystallis, which means ice. Just for information, so ice is symmetrical, it's a crystalline substance. So crystal, same thing. Alright, so crystal, so how do we study crystal? So that's the major questions that we have. That's the major question that we have. There is a particular science that is devoted to crystal, that is known as crystallography. Remember this. So crystallography is a different science altogether, which is devoted to studying crystals. So what happens in crystallography is, we study crystals, we study the arrangement of atoms, how the atoms are arranged. So this is a whole science that deals with it. And in this, what we also do is we study the structure of atoms, molecules, how arrangement of atoms are done, the bond length, everything is done in this crystallography. So there is a technique in this which is known as X-ray diffraction. So that's the major technique. What happens in this, I'll explain you just after explaining this. So what happens in X-ray diffraction is we study, so the question is, how do we know the bond length? You see in your books, right, the bond length, the bond angles, the different huge molecules like biomolecules, proteins. How do we know about their structure? This is the method. So crystallography is the science, X-ray diffraction is the method by which we know the bond angles and the arrangement of atoms, arrangement of molecules in the whole structure. That's how in your books you see DNA structure, biomolecule structure, protein structure. This is how it is done. Right? You get the answer to the question, because we don't understand where do these figures come from. This is how it is done. So X-ray diffraction, what happens in X-ray diffraction? X-ray, we know what X-ray is, the one that we use in for medical purposes, for getting our X-ray. And diffraction for now just remember, diffraction is bending of light. You'll study about it later when you study physics, diffraction in physics, so bending of light. So that's what diffraction is. What happens in X-ray diffraction technique? So there is X-ray. So X-ray is fired at a crystal. So this is a crystal. So some of it gets transmitted. So this is X-ray. Some of it gets transmitted. I mean most of it, almost 90% of it. And the remaining is scattered. So this is scattered X-ray. And this is transmitted. So this transmitted one we use for medical, the medical X-rays that we get. This is how we get. So here in place of crystal we have our body. So X-ray strikes our body and then we get the X-ray that is there. In case of crystallography, X-ray diffraction, what happens is, scientists, they use this scattered X-ray, they use it, they collect it on a screen, and then they study the waves that they get, because interference is what happens. Interference is mixing of waves. So these scattered waves, so they mix and they form a pattern. So this pattern they study, then they get different things like bond angles or different bond lengths. So this is how they determine all the structures of the biomolecules, the DNA, the proteins, everything. use this technique, X-ray diffraction. There's a technique that they use. And now I want you to remember this name, Lawrence Bragg. So he in 1915 got Nobel Prize for this technique, X-ray diffraction. He perfected this technique. He did not invent it, he perfected this technique. Lawrence Bragg. So he got in 1915, he along with his father, Mr. William Bragg, got Nobel Prize in physics for X-ray diffraction technique. And the best part is he was only 25 years. Mr. Lawrence Bragg, he was 25 years when he got Nobel Prize. That's an amazing thing to achieve. You know, at 25 years, he's the youngest physicist to get the Nobel Prize. So he got it in 1915 along with his father. Now some might say that his father did most of the work, he was just an assistant. No, he did most of the work. His father just guided him. Alright. So Mr. Lawrence Bragg in 1915, he got the Nobel Prize. After Lawrence Bragg, the youngest physicist that we have is Mr. Werner Heisenberg, the one from Heisenberg uncertainty principle. So he got it at 27 years. So we have young physicists that got Nobel Prize at that time. Alright. So now I want to mention two crystals that I want you to look up. So go online and search for these two crystals. So one is selenite and the other one that we have is pyrite. So selenite, we have 11 to 14 meters high. That's how high these crystals are, 11 to 14 meters. You just imagine how tall these crystals are. Alright. So these are found in Mexico. There are caves in Mexico where they are found. Now pyrite is also known as fool's gold. Fool's gold because of its color. So pyrite are these beautiful cubes, golden cubes that you have. So that is pyrite. So these two crystals, so these are naturally occurring crystals. What are crystals again? Crystals are solids that have regular arrangement. There's symmetry in their arrangement. So that's what crystals are. So these are found naturally. Just imagine how beautiful artist nature is. It creates these beautiful big crystals, 11 to 14 meter. Pyrite, this looks like gold. We call it fool's gold as well. Just go online and click on images. Once you type pyrite, then go to images. You will see this beautiful structure, this cubic structure, and it is also known as fool's gold because of its color. And selenite, it's huge crystal. And nature has its own artistry going on. So just look for these crystals. So crystals are also useful. You might have seen like many people interested in crystals. So these are the same crystals. So whenever you see crystals, crystals are solids which have arranged structure. They have arranged structure. That's why they are known as crystals. Alright then. So now we have studied a bit about crystals. Now what we want to do is we want to go inside the solid. That's what we want to do. Alright. So what we want to study is we want to study how atoms are arranged inside the solid. Now I want you to remember this. There has to be no confusion here. What we are doing is we are studying crystals. We are studying the arrangement of atoms or molecules or ions in the crystals. So we are not studying amorphous solids. We are only studying crystals. The reason being, crystals have ordered arrangement. That's why we can study them. Amorphous solids, they don't have any order. So we can't study them. We can't generalize their properties. So we can only study crystals. So before moving on further, so what I want to do is I want to introduce few terms regarding crystal. So this is crystal lattice, or we also call this as space lattice. So what is a crystal lattice? So before going on to crystal lattice or space lattice, What is a lattice? We need to know that. So lattice is arrangement, regular arrangement of points in 2D space. So that is what a lattice is known as. That's a 2D lattice. So let's say we have this arrangement. So what is the arrangement? So we have regular squares. We have squares are regular. So we have squares arranged here. So that's a lattice. So I can have it this way, this way, this way. So that's a 2D lattice. So when we have 3D arrangement of points in space, that is known as crystal lattice or space lattice. Remember this, 3D arrangement of points in space is known as crystal lattice, and that is what a crystal is. Or space lattice or crystal lattice is what a crystal is. Alright? So as I was discussing this, so if I have something like this, you see, I have in this way, I have crystal lattice. So I have 3D arrangement of points in space. I can have it upward, sideways, downward. So I can extend this the whole way. This whole crystal lattice that is there. Alright. So now the smallest part of the crystal lattice is what we call unit cell. Remember this. The smallest, so what would be the smallest portion of this crystal lattice? This would be the smallest portion. This. So this is what we call a unit cell. How do we define a unit cell? The smallest portion of the crystal lattice, which when repeated in all the directions gives the whole crystal lattice. So if I repeat this upwards, sideways, downwards, it will give me the whole crystal lattice. Alright? So there should be no confusion. What we are doing, if this is a crystal, this chalk box, if this is a crystal, inside crystal there's crystal lattice. That is, the points are arranged in 3D space, which is crystal lattice. What are the points? The points are either atoms, molecules or ions, whatever they might be, and in that we have a smallest portion of the whole crystal lattice. There is the smallest portion which when repeated in all directions, it gives me whole crystal lattice. What is the smallest portion known as? It is known as unit cell. Alright, simple definition. Don't get confused. Remember what we are doing. We are studying solids. Remember this. It's not all about marks. It's about what you are doing. Know about it. Alright, so this is what we see in our surroundings. We are studying nature. Alright. So this is what crystal lattice is, and few things to remember. So each point in the crystal lattice or space lattice is what we call a crystal site. Crystal site, or we call it as lattice point. What does this crystal site represent? They represent the constituents of which the whole solid is made up of. Either it can be ions, atoms or molecules. Alright. So we have this, and also just remember, so these lines are not actual lines. So these are just representations. Remember this. Like we used to draw bonds. Are the bonds actually there? The diagrams where we show like carbon-oxygen bond in CO2, they are just diagrammatic representation. Just remember this. These are not actual bonds that are there. Alright. So let's discuss the unit cell in detail. What is a unit cell and what are the type of unit cell? How do we characterize a unit cell? So we have to have some characteristic which defines a unit cell. Alright then. So unit cell. So unit cell okay, so this is a unit cell. So how do what is unit cell again? the smallest portion, which when repeated in all the directions give the entire crystal lattice. So how do I characterize this unit cell? What does that mean? So let's say if I have the table here, how do I characterize the table? How do I know this is a unique table that I have in front of me? Its length, its width, its height, these are the characteristics that define the table uniquely. So in case of a unit cell, the characteristics that define the unit cell are 3 edge lengths, which are A, B, C, and 3 angles, which are alpha, beta, and gamma. Alright, so now you see a box here. It's a cube. Alright, so how do I name this cube? Just see how do I name this, because this will remove all the confusions that you might have. So there are crystal systems that we'll be studying after this. So there's confusion while it comes regarding the shape and how the structures actually are. So just remember the convention that I'm using. You won't have any confusion after this. Alright, so ABC. So this, the back horizontal line is A, this is B, and this is C. Remember this. There should not be any doubt. A, B, and C. Obviously this one is also A, this one is also B, because this is B, this is B, and C, this one is also C. Same goes for up, and same thing. Alright, so now talking about angles, so just see how easy is it. It is regarding angles, so alpha, beta, gamma. So when we are talking angle between A and C, we'll forget the corresponding ones. We'll forget alpha and gamma. So for A and C, what we have is beta, sorry. Alright, so the angle between A and C is beta. What's the angle between A and B? A and B, I forget the corresponding angles. So this is how I forget it. Gamma. A and B, I have gamma. And obviously between B and C, that's the remaining angle, which is alpha. That is the angle that we have. Alright, so just to remove any confusions, I'll just magnify this thing. Magnifying it here. This is A, this is B, this is C. So angle between A and C is beta. This is alpha. And A and B is gamma. Perfect. And these edges, they don't need to be perpendicular always. So obviously these alpha, beta, gamma, they can have different values, and ABC, they can have different values, as you will see later on. As you will see in crystal system, all the values that they have are different one. Perfect. And before we proceed, so I just want you to look at this. So this alpha, beta, gamma, so these are Greek letters. Remember this? So Greek alphabets. These are 24 in numbers. Like in English, we have 26. What I want you to do is go online and search for Greek alphabets and just go through these alphabets. So you will see alpha, beta, gamma, then delta, epsilon, then we have omega. These are permittivity. For permittivity, we have epsilon. So these are all symbols that are used. So these are very often used, frequently used in physics. You will find these symbols. So just go through these 24 letters so that you get a hold of what actually the Greek letters are, so that when you study physics, you don't feel alienated with the symbols that you see. You know that these symbols are Greek letters. Alright, so because what we have is we have A, B, C, the English alphabet, and then we have Greek alphabets. These are all the symbols that we have, and also we have capitals and small. So these are the only things that we use in physics, because we don't have many letters. Alright, so this is everything that is there. So just go through the Greek alphabets, go online and search for these, and get a hold of this, get a grasp of the Greek alphabets that are there. Perfect. So now what we want to do is we want to discuss the different types of unit cell that are there. Let's do that. So unit cell is the smallest portion of the crystal lattice. Alright. So now, what are the types of unit cell? We have primitive, and the second one that we have is centered. Alright. So what is primitive unit cell? In case of primitive unit cell, we have the constituent particles, which are either atoms, ions, or molecules, only at the corner. Alright, the unit cell, we know what a unit cell is. So the atoms or molecules or ions will be present only at the corner. Let me show you. Okay. So this is what a primitive unit cell looks like. Atoms, molecules, or ions, only one of these. Either atom, either molecule, or either ion, which are also known as constituent particles. They will be present only at the corners. So this is what primitive unit cell is. Now in case of centered, what centered says is the atoms are present not only at the corner, but they are present at centers as well. That's why the name centered. How many types do we have? We have body centered. Then we have face centered. And the last one that we have is end centered. So what is body centered? So in case of body centered, in addition to the corners, so because it's a unit cell, so you will have the atoms or molecules or ions at the corners as well. In addition to that, we will have at the body center as well. That's why body centered. Just whole body, at the center of the body, you will have one more unit cell, one more constituent particle. So in case of face centered, you have at the corners and at the center of the face as well. So how many faces do we have? 1, 2, 3, 4, 5, 6. So 6 faces. At the center of each face will have one more constituent particle. Alright, so the last one is end centered. We'll have at the corners and we'll have at one of the two opposite, the pair of opposite faces that we have. So let's say in this case end centered, we have one pair, this, or either left right or either front of center. Alright, so either of the pair, the constituent particle will be there. So let's say if I have it here, the other has to be here. That's it. Now if I have it here, the other has to be here. So two opposite faces it has to be there. It can't be here and here. Alright, so that's wrong. It has to be any two opposite faces. If it is here, the other one would be here. So that's why it is known as end, only at the ends. Alright. So these are the classification of the unit cell. Now what we are going to do is we are going to study the types of primitive unit cell. Alright, perfect then.